Alright, so we're looking to conclude our chapter dealing with accelerated motion. Um, we're now calling this chapter 3 of the textbook we're currently using. So we're going to finish this by reviewing our discussion of freely falling objects. Now, for the assigned readings of this PowerPoint, you can either choose to read the section on free falling objects on your own in full, or I've broken it into separate chunks that you can read those sections and just go ahead and pause the video and read up on the material before you continue on. But I do want you to read starting with that intro paragraph on page 72. I will have this PowerPoint available on Edline if you would like to go ahead and view the various video demonstrations I've placed on here. The first one I have is just simply dropping a baseball and a piece of paper. Think about what would happen if you just dropped a plain piece of paper and a baseball. And then what if you crumbled up that same piece of paper and dropped the baseball? How would their motions compare when you drop them? Finally, the other demonstration in that video, and you don't have to watch the whole thing. The point of it is just to see the demonstrations. The teacher places a piece of paper on top of the book and drops both at the same time. He also places a sheet of paper underneath the book and drops them both at the same time. Just got to predict how the two would fall compared to one another, because these are just kind of ways to get rid of the air resistance that's preventing the paper from falling at the same rate as the book. Because as we have discussed, air resistance causes objects to fall at different rates based on their size and other factors about the object. Well, just a definition here. Free fall. When we discuss free fall in this class, we have to remember that it's the motion of a body due to gravity alone. That's meaning no other forces such as air resistance are acting on it. And we know that this isn't very common in real life, but most of the objects we deal with, the air resistance is so negligible that we can treat it as it follows the same properties of an object in free fall. So our objective for learning today, we want to be able to define the acceleration due to gravity. We also want to solve problems involving objects in free fall. So just a background review of freely falling objects. I've included another video in the PowerPoint that you can watch on your own if you'd like, just to kind of let you visualize Galileo's experiments. What he essentially did was, since it was hard to measure the free fall of certain objects, especially with the time equipment that was available to Galileo at the time, he used inclined planes, realizing that objects would also accelerate on inclined planes in much the same way that they do when they fall. He used inclined planes to kind of dilute gravity's effect and observed phenomenon that way. But if you would like more details, you can go ahead and look on YouTube. There's various videos that explain that further. He also has his famous leaning in tower experiment, where he tested the hypothesis that objects of different weight fall with the same constant acceleration. Again, for 2,000 years before Galileo, the thought had been that heavier objects wanted to fall faster than light objects. Galileo kind of crushed this idea with the legend of this Tower of Pisa experiment. He had also hypothesized that given if there were a way to delete the effects of air resistance, something that like a feather that was light and would undergo much air resistance would fall at the same rate of something like an apple. And at this point, if you want to go ahead and read Acceleration Due to Gravity on page 72 in your book, you can go ahead and pause the video if you choose to do that now. But notice in this picture, and I also have a link to a Mythbusters clip on this if you'd like to watch it. The acceleration of the feather and the apple. This is actually in a vacuum chamber where the air has been evacuated, taken out of the chamber. Notice with no air resistance, a picture is taken every second of the apple and the feather. Notice that they do fall at the same rate. So one thing to kind of remember, it's easy to think of an object in free fall as something that's just falling. However, an object is in free fall as soon as it's released, whether it's going up or it's coming down. So even if you're throwing an object up in the air, that path that it's taking upward is still considered part of its free fall. The entire path of its upward and downward motion is in free fall. It's following the same effect of Earth's gravity. And that acceleration due to gravity on Earth, we call it the symbol G. The value for it is 9.81 meters per second squared, though this value for G does depend on the latitude that you're standing on Earth. We'll discuss where G comes from later in the course, but for now, we can just assume it as 9.81 meters per second square, about an average latitude for most Earth surfaces. Now, what's very important is you want to make sure when you're solving problems involving free fall acceleration, you want to make sure you're defining your axes appropriately. So if you call up the positive direction, then your acceleration is going downward because it's speeding up as it goes down. So since if up is your positive, your 9.81 meters per second squared must be negative. On the other hand, it is helpful if you're only worrying about dropping something. You don't necessarily have to call up your positive direction. You could also call down your positive direction, and in that case, 9.81 would be positive, and of course any upward velocities would then have to be negative. Just make sure it doesn't matter which sign you use for your acceleration, as long as you're consistent. In other words, opposite directional velocities must have the opposite signs, and velocities moving in the same direction as the acceleration must have the same sign as that 9.81. We'll see that in action in some of the problems we do for examples. Again, it doesn't matter what you choose as long as you're consistent. So let's take a look at this ball that's being dropped here. Again, a picture being taken every second of that ball's free fall. So let's think about what would the ball's speed at each position be if a picture was taken each second. If it starts at rest, after the first second, since it's gaining 9.81 meters per second, its speed should be 9.81 meters per second. And after second 2, you should add another 9.81 meters per second. You should end up getting 19.6. You're adding about 10 meters per second each time, since we can sort of round up 9.81 meters per second. You end up with 29 after 3 seconds, 39 after 4 seconds, 49 after 5, and so on. So we get up to about 59, 69, 79, and we end with a final speed of 88.2 meters per second. But let's think about this the other way. What if I had thrown the ball upward at a speed of 88.2 meters per second? Wouldn't the ball still follow that same path, starting at 88.2 meters per second, slowing down about 10 meters per second each second, and ending up at rest at the very top of its path? So again, free fall is going to follow the same path downward as the opposite path if it were to be thrown upward. So let's look at an example problem here. Let's say a person steps off the end of a 3-meter high diving board and drops to the water below. How long does it take the person to reach the water? What is the person's speed on entering the water? So here it's a simple problem where the diver is stepping off the board. There's no upward and downward motion. So let's just go ahead and call the downward motion positive, since all we're dealing with is a straight downward path. So let's look at what we know in this problem. So we know that the distance traveled is going to be 3 meters. We know that the acceleration due to gravity, since we're calling down the positive direction, is going to be 9.81 meters per second squared. We want to know, first of all, the time. There is usually one other piece of information that's not given in a lot of problems that you automatically know, and that's your initial speed. In this case, he's stepping off the end, so his initial speed is going to be 0 meters per second. To find that time, we can look at our equations we have on our card. We should have 4 basic kinematic equations. One of those being delta x equals VIT plus 1/2 AT squared. Again, we're solving for t. So let's go ahead and we can say this is 3 meters equals 0 times t plus 1/2 9.81 t squared. This term's going to cancel out. It's 0, so we end up with 3 equals 4.9 t squared roughly. We'll divide both sides by 4.9. We get t squared equals 0.612, which means t equals the square root of that, or 0.782 with 3 significant figures seconds. So now the second part, part B, let's see if I can clear my writing here. Part B wants to know, what is the person's speed on entering the water? So now we know that the time again is 0.782 seconds. Still have the previous information from before. One thing we can use for speed is our equation V. F, or the V at a certain time, is equal to V initial plus AT. Again, we try to find this final velocity. We know our initial speed was 0. We're using positive 9.81, and our time is 0.782 seconds. So we multiply those two. We get our final velocity equals 7.68 meters per second. So now I have a problem that I would like you to try on your own. You can go ahead and pause the video here. I am going to flash the answer rather quickly after these on your own problems, so if you want to just go ahead and pause it and try to solve it. It's asking, what is your speed on entering the water if you step off a 10-meter diving tower? You should get an answer of 14.0 meters per second when you solve this out. And you can go ahead and include this on the back of your